So we are working on discussing queuing models, right? And the simplest one was MM1, infinite system, and simple extension of the MM1 queuing system was MM1 B plus 1 system, right? So we discussed about that, and I mentioned about lambda effective. Okay, so as long as we have finite capacity, okay, some blocking event occurs. Blocking event means even though someone arrived to the system, but he or she cannot enter the system because the system is full. Okay, so we need to think about actual arrival rate. Actually, we can think about thinning process. Okay, we can just exclude all the blocking events, and then based on all the available events, we can construct another Poisson process with rate lambda effective, not just lambda. Okay, so actually inside the system, okay, we can observe the arrival process with lambda effective, right? Today we are going to talk about a different type of queuing system. So far we discussed a single server, okay, single server. But what if we consider the system with multiple servers, okay? But multiple servers means all servers can perform the same. Performance of all the servers are the same. So we call this identical servers. Okay, identical server, and they are not cooperating each other. That means parallel servers. Okay. Actually, in practice, we cannot see such situation with we have different servers, and all the servers has the same ability. This assumption is quite unrealistic, right? But when we consider it's kind of internet internet service system like Google, okay? Then when we apply how fast we can access to the system, or how fast we can use some internet service is like based on such a system. Okay, we can analyze the system with queuing theory, and in this case, servers is kind of internet server system, kind of machine. Okay, so let's consider M infinite system. Okay, this infinite means infinite number of parallel and identical servers. Okay, but actually this one is also not realistic, even though this one we consider internet service systems, because infinite number of servers impossible, okay, in practice. But some of the main search engines or corporations, they install a kind of large server, okay, large server can handle many customers or some servers, okay. And we can assume that this capacity of this server is kind of infinity, because enough for handling all the servers. Okay, so let's consider this case. X of t represent number of customers at time t. Okay, in the system. Okay, how can you define state space S? 0 to infinite. All the integers from 0 to infinite. By the way, you can see all these materials in your reading material, the same. So you can check. To calculate long-run average numbers or some probability in the limit, okay, we first need to figure out generator matrix, okay, generator matrix, because arrival times, inter-arrival times, and service times are exponentially distributed. We can model this with a continuous time Markov chain. Okay, so analyzing this system is the same as analyzing a type of continuous time Markov chain. Okay, so how can you draw rate diagram? 0. So we can put the node first. 0, 1, 2, 3, and so on. Okay. What is the rate from state 0 to 1? Lambda. 1 to 2? Lambda. 2 to 3? Lambda. When we increase by 1, the rate is lambda. How about 1 to 0? Mu. Okay. How about 2 to 1? 2 times mu. Because, yes, 2 servers working at the same time and minimum of 2 exponential mu, right? 3 to 2, 3 times mu. And so on. By the way, do we need buffer in this case? Waiting line? What do you think? No, we don't have to consider waiting line because we have infinite servers. As long as a customer arrives to the system, instantly, immediately, he or she can get his or her services. Right? Okay. So rate diagram is here. And then, can you calculate stationary distribution? Yes. So, as we did last class, we are going to use cut method. Okay, cut method. Okay, note. Outflow equals inflow. Zero, 1, 2, and so on. So for node 0, outflow is lambda times pi 0 equals inflow is mu times pi 1. Okay. How about node 1? Lambda plus mu times pi 1 equals lambda pi 0 to mu pi 2. Okay. And then when we put this instead of this, okay, we can simply get mu times lambda times pi 1 equals 2 mu pi 2. Okay. We can just subtract left hand side and right hand side. Okay. This one. They are the same. Okay, cancel out. And for node 2, lambda plus mu pi 2 equals, is it correct? 2 mu. Okay. 2 mu pi 2 equals lambda times pi 1 plus 3 mu pi 3. Okay. And then also we can put this to this, right? And then cancel out. Then we can get lambda pi 2 equals 3 mu pi 3. Okay? So by induction, you can derive a kind of rule to represent pi sub k. How can you do that? So based on this, pi 1 is lambda over mu pi 0. Okay? And how about this? Pi 2 is lambda over 2 mu times pi 1, right? And pi 1 is lambda over mu pi 0. Okay? We can rewrite this like a half times lambda over mu square pi 0. Okay? We can do one more. Based on this, pi 3 is lambda over 3 mu. Okay? Pi 2, right? And this one is the same as lambda over 3 mu times a half times lambda over mu square pi 0, right? And this one is the same as 3 times 2 times 1 times lambda over mu cube pi 0. How can you write this 3 factorial using? Can you generalize this? So as long as we know the pi 0, right? Then pi k might be 1 over k factorial lambda over mu to the k's power, and then pi 0. Okay? And we have one more condition. Which what is that? What is this? Summation for the k is from 0 to infinite, right? 0 to infinite, because we can consider infinite number of states. Okay, 0 to infinite. Pi k is the same as pi 0 times summation of k 0 to infinite 1 over k lambda over mu the k's power. K factorial. Okay. Okay. So is there any idea how can we rewrite this with a function we are familiar with? Exponential. This is kind of Maclaurin series or Taylor series of exponential function, right? This one is the same as what? E to the negative lambda over mu. Okay? Sorry, e to the lambda over mu. Right? Lambda over mu. This one should be the same as 1. Right? So, pi 0 is e to the negative lambda over mu. And pi k is 1 over k factorial lambda over mu to the k's power e to the negative lambda over mu. So is there any comment about this distribution? So stationary distribution can take 0 to infinite, right? This random variable, we can consider a certain random variable with pi k, okay? Pi 0 to pi k. And the probability that this random variable is the same as k is 1 over k factorial times lambda over mu to the k's power times e to the negative lambda over mu. What do you think? A random variable is the same as k. Probability that a random variable is the same as k. This one is discrete random variable, right? And PMF is 1 over k factorial times constant to the k's power times e to the negative the constant. What do you think? Have you ever seen such distribution? We mentioned this distribution many times just before CTMC. What do you think? Poisson. This one is PMF of Poisson distribution with rate lambda over mu. Okay, you can check. Okay. Do you see what I'm saying? Okay. So if time t goes to infinity, okay, time t goes to infinity, number of customers in the system, okay, this number of customers in the system follows Poisson distribution, okay, with infinity. Infinite queuing system. Of Poisson random variable with lambda over mu. Okay. Then can you calculate long run average number of customers? What do you think? Yes. Can you calculate it instantly? Yes, lambda over mu. Because this one is exactly the same as expected value of Poisson lambda over mu. Right? Because limit this n limit t goes to infinite 0 to t x of t dt, and this is the same as summation for k from infinite k times pi k. This one is actually the same as expected value of Poisson lambda over mu. So you don't have to calculate it since we know this Poisson mean value of the Poisson lambda over mu is the same as lambda over mu. Let's think about stability. Stability, okay? Lambda, if lambda is 10 customer per hour, okay? And mu is 1 customer per hour, is it stable or not? Unstable? Really? What do you think? Unstable means system explodes. But as I mentioned before, do we need any buffer? No. As long as someone arrives to the system, he or she can get service instantly. Okay? Quite tricky. Even though service arrival rate is quite larger than service rate, but this service rate is for just one single server, and we have infinite servers. So actually, we have infinite capacity for service. Okay. So this system is always stable. No one needs to wait. Just he or she can get the service right away. But this one is quite unrealistic, right? Unrealistic. We cannot install such infinite amount of servers in practice, in world. Okay? So we need to think about that. What if we consider we have large number of servers, large enough, okay, but not infinite, then what happens? No waiting time. Let's say we have 100 servers, okay, but still we have a chance, even though this is rare, right? Rare. We have a chance. Someone cannot enter the system, or someone cannot the service and just leave the system because we just have 100 servers. Okay. Then how can you calculate the blocking probability? Let's consider we have 100 servers. How can you calculate blocking probability? Capacity is 100. Based on the structure. Based on the structure, how can you calculate? So assume that we have like large K number of servers. Okay. Then after, so all K servers are working. Then after that, before someone leave, okay, another enter the system. Then what happened? He or she cannot get his or her service and just leave the system right away, right? We need to calculate this probability. So what is the probability that this x of t, if t goes to infinite, so let's say infinite, okay? This one represents long run, if t goes to infinity, the stationary distribution is k. Well, if this one is equals k, then this one represents stationary distribution of x of t, okay? What if this one is greater than, okay, large k, okay? This one is blocking probability, right? With this probability, we cannot enter the system, right? This one is actually the same as 1 small k is from 0 to large k, probability that x of infinite equals small k. Okay, we can calculate it. So by the way, in your reading material, okay, if sure. So let's say with some lambda and mu, and for large k equals 100, we can get the number 0.1. You can calculate it because we have how to calculate. Okay, right? Since we have, as long as we have lambda and mu, okay, and large k, we can calculate it, right? It takes some time, but you can use calculator or some program language. Okay. Let's say this one equals 1.1. That means one out of 10 customer cannot enter the system on average. Okay? On average. Okay. So we can calculate blocking probability with this formula and station distribution of infinite queen system. And when you try to design the system, we can target this number. Okay? Even though we cannot install infinite servers, but we want to know how many servers do we need to install with blocking probability is a certain number. Okay? Let's say when we try to design such a server system, let's say, what if we control this probability like 0.02? 2%, with 2%, someone cannot enter the system. That's fine. In practice, when we make a decision like this, okay, even though we cannot install all infinite servers, we need to think about this in practice. But 2% is okay. Then, based on the number, you can calculate k when you solve the equation. Right? Let's say this one is 250. Then, based on the structure, we can suggest that 250